So let's say we had a curve on the xy plane C, right? So this curve is just on the xy plane. And let's say we had a surface kind of over it, right? Some surface f of xy. Now, what you'd imagine is, this obviously the surface is going to kind of extend, like a sheet of paper, right? But there's going to be kind of a curve on the surface that lies directly above the curve on the xy plane, right? It's going to have all points. It's going to be all points directly above that curve. What you can do is you can find the area kind of underneath that curve. If you were to think of, underneath that curve of the surface, you kind of think about like a curtain, right? Like a curtain, that you're finding like the area of like a curtain or like a fence, right? And we can do that with the line integral. And I think the intuition is pretty simple, right? If you imagine a small little section ds, right, along the curve that kind of represents our, width, and then the height just ends up being f of xy, right? The function value at that point. So to find the area, you're just integrating all of that, right? F of xy ds, and then we use the integral, and then we use a c to indicate that it's like a line integral, right? So how do you solve a line integral? Well, what you kind of have to do is you kind of have to treat this curve right here as you have to parameterize it, right? You can say that, hey, this curve is going to be, there's going to be x of t and y of t, and that defines the curve along the, xy plane. And then what you realize is, okay, well, what is ds? Well, remember, if you think about just basic intuition, right? We know that ds dt is going to equal kind of the velocity, I guess, of the curve, right? Like if you think about, and I should really put ds here. It's really a ds here, right? ds times height. ds dt, well, that just ends up being the square root of, right, this is just the magnitude of, like, if you think about position vectors, this is just the magnitude of the velocity vector. So this is going to be kind of, do I use partial? I forget, no, I don't use partials, because it's going to be, these are just functions, right? dx dt squared plus dy dt squared. So hey, what is ds equal to? ds is just equal to square root dx dt squared plus dy dt squared dt. So I can substitute that in for ds, and really I'm going to be doing the area. It's going to be the line integral. If you think about f of x of t, y of t, square root dx dt squared plus dy dt squared dt, right? You can think about the arc length, formula, right? This is just the arc length formula. We're just adding on that multiplier being the function value. So let's try this in action. Part A, we want to evaluate this line integral, x sine y ds. That's the integral we want to really take. So to think about this, right, first we got to parameterize the curve. It's going to be a line segment from 0 to 3, right, to 4 to 6. Well, we know from, if you go think way back to maybe chapter 12 or 13, I forgot, I think it is chapter 12 when we, I think it was chapter 12. I don't remember. I think it's chapter 12. We were able to parameterize curves, and what we kind of said, that's the chapter 12 thing. And what we did is we kind of said, okay, well, it's going from 0 to 4, but x value is going from 0 to 4, and the y value is going from 3 to 6. So what you could say is x is equal to 4t, and then y is equal to 3t plus 3, right? And this is all from 0 less than or equal to t less than or equal to 1. And, you can think about it, right? From after 1 second, it's at, when you plug in 4, you get 4, and then at 1, right? I see that it starts at 3, so that's kind of like my, y-intercept, like my plus 3. That's because it starts at y equals 3, and then we have, in 1 second, it goes up 3, right? You could technically do, you could technically do t squared, right? You could make it a t squared or t cubed, but you don't need to, right? You can choose how you want to parameterize it so long as it only travels along that curve once, right? Might as well make it so that I'm dealing with simple derivatives here, right? Because what is, if I think about what is, square root dx dt squared plus dy dt squared, well, that's just going to be equal to square root 3 squared, or 4 squared for x plus 3 squared, and that's just a Pythagorean triple, so I'm going to get 5. Now, let's take the line integral. So I'm going to have line integral x sine y ds, and we just got to replace everything in terms of t. So I know x is just equal to 4t. So I'm going to have integral 4t times sine y, so sine 3t plus 3. And then we are going to have times 5 dt, right? Times the square root dx dt squared plus dy dt squared. That just ends up being 5. So I can pull the 5 out of the integral. And what are my bounds? Well, I'm going from 0 to 1. And I can also pull a 4 out of that. So I get 20, right? I can pull the 4 out in front. I'm going from 0 to 1. This looks like kind of a nasty integral, but in reality, you could use like the integration by parts, right? So you can say, hey, let u equal t, let dv equal sine 3t plus 3 dt. If I were to take the derivative of u, I get du is equal to 1 times dt. If I take the integral of dv, right, I get v is going to equal, you just have to kind of use reverse chain rule, right? So you kind of see there's a 3t plus 3 in there. So it's going to end up being 1/3. It's going to be negative 1/3 cosine 3t plus 3, right? Because when you take the derivative of cosine, you get negative sine. That takes care of the negative, and then you're going to have to multiply by 3. You're back with where you started. So I'm just going to like kind of do a general so integral sine t times sine 3t plus 3 is just equal, or dt, oh my gosh, is just equal to, and this is just the antiderivative, I'm not taking the definite integral, but it's going to be uv, so negative t over 3 cosine 3t plus 3, and then we're going to do minus integral, and then I'm going to be taking the integral of negative 1/3 cosine 3t plus 3 du, which is just dt. So this, okay, negative t over 3 cosine 3t plus 3. I'm going to be taking, so if I take the derivative of negative sine, I get negative cosine, right? So this I can really put, it's going to be plus 1/9 sine 3t plus 3. Does that seem right? I think that seems right. Right, yeah, that seems right. Okay. So then I can do my Liate. So when I do my Liate, or not Liate, what am I talking about? I'm just going to set this equal to area. So when I do this, I'm doing from 0 to 1. So it's all of this, really. My area is just going to be all of this times 20. So I guess I'll divide it by 20. I don't know, I'll just do this like this. So area is going to equal 20 times negative t over 3 cosine 3t plus 3 plus 1/9 sine 3t plus 3. Hopefully I'm doing this right. It's going to be really embarrassing if I'm not, from 0 to 1. And so, about 20. So when I plug in 1, excuse me, when I plug in 1 for everything, I get 1/9 sine 6 minus 1/3 cosine 6. And then when I plug in 0, that just becomes 0. So I'm just going to be doing minus 1/9 sine 3. So this is kind of a weird answer. Let me double check with the key. I might have done that completely wrong and I wouldn't even know. Now where is it? Okay, I did do it right. I think. I'm pretty sure I did do this right. You can factor out a 1/3 and you're left with negative cosine 6. You would be left with 1/3 positive sine 6, and you'd be left with okay, perfect. So kind of a weird answer, but there you go. That's how you can take line integral. Not too bad. You just have to do the integration by parts. But let's go on to part B, and you notice we're not doing ds, we're really doing dx, right? But if you think about what is dx, well, right, if I'm doing z times dx, think about it, right? I know dx dt, right? So I know dx dt is equal to x, or it's going to equal, whatever the derivative is, x prime of t. So I know dx is just x prime of t dt. So it's not too bad, right? I just substitute that in for ds. And notice the notation is a little funky because it's like, oh, I'm doing line integral of, dx, and then I'm doing line integral, like it's like z dx plus x dy plus, we don't really, why do we have multiple dx, like what? Really, this is just, a quick way to say I'm summing up the sum of all of these, right? If I were to take the same line integral over the same curve. So they give us the equations for the curve. So that's actually pretty nice. And what I can do is I can just do, right, okay, so this is going to equal integral from 0 to 1, right? So z times dx, well, dx, right, is just the derivative times dt. So first I'll substitute in z. So z is going to be t squared times, I'll do this all in parentheses, t squared times the derivative of x is 2t. So it's going to be 2t times dt. I'll save the dt for the end, right? Because all of them are going to have a dt. Plus x dy, x is t squared. The derivative of y is going to be 3t squared. And then y dz, y is t cubed. Derivative of t squared is 2t. All of that dt. So let's just simplify this, right? So area is equal 0 to 1. So I get 2t cubed plus 3t to the 4th plus 2t to the 4th dt. So this is going to be the area is going to equal, so I'm going to have 1/2 t to the 4th, right? I'm just doing reverse power rule, plus 3/5 t to the 5th plus 2/5 t to the 5th. I'm going from 1 to 0, and obviously if I'm going from 1 to 0, when I plug in zeros, I'm going to get 0, right? This is all polynomial. When I plug in 1, it's just going to be the coefficient. So the area is going to be 1/2 plus 3/5 plus 2/5. So if we just multiply this by 5, and then this by 2, I get 5 plus 6 plus 4. So this would be, no, this is not, wait, what? It shouldn't be 1. Hold up, did I do something wrong? Where did I mess up? Where did I mess up? Is it 1? Because I get 2 over 4, 3/5, 2/5. Or no, I guess it would be 15 over 10? That doesn't even make sense. This is just 1. Oh, so it should be 3/5. What is the answer? Is it 3/5? Or, sorry, is it 3/2? Is it 3/2? Oh, it is 3/2. Okay, I get 15 over 10, which is equal to 3/2. Cool. All right. Now I want to talk about vector line integrals. So we've been working with scalars. Now, let's say, so what we know, so for vectors, if we want to do the same thing for a vector field, right? So remember a vector field, if you were to, draw one out, let me just erase all this. If I were to draw a vector field, it would look something like this, right? There's going to be vectors, mapped out, and it by a function, right? A function would determine the direction and magnitude of these vectors, right? So if I want to find, let's say I go on a path like so. We'll call this a curve C. Now, what you're gonna, let's say, just for funsies, I want to figure out, okay, let's do it like this. I don't want to bring in physics just yet. Let's say, you know, there's going to be an element ds right here, right? And if you think about the curve, this ds we can actually represent as a vector, right? This small little kind of displacement, right? ds, right, or we can call it dr, the displacement, right? The small displacement is going to equal the tangent vector to the curve ds, right? Let's think about this, right? The tangent vector is the unit tangent vector. You just multiply by the magnitude of ds and you get dr. The magnitude of the displacement is ds and the direction is just a unit tangent vector. Now, let's say the vector, the curve, let's say the vector field is given by f. And I want to find f dot dr, right? So if this is my vector field, and then this is the displacement, this is just a simple displacement along the curve. This is just a simple dot product, right? And what I can do is I can integrate along the curve, and then I can find the total of this summed quantity. Now you might be saying, hey, like, what's the point of this, right? What is this? Why would I ever want to do this? Well, hey, in physics, if you've taken physics 1 in college, right? If you've taken calculus-based physics or physics C, this is a definition of work, right? The definition of work is it's the total kind of, if you were to sum up all the dot products, you get a total dot product, and this ends up being the definition of work, except not as vectory, right? You don't see the line integral notation, but this is the definition of work. Now, as you can imagine, we know, hey, dr, I'm going to do this a more formal way, but there's a more obvious way. We know that dr is just t times ds, but we also know that, well, hey, the tangent vector, the way you can find the tangent vector is it's just by doing the second derivative of position over the magnitude, right? That's how you find the unit tangent vector, because the tangent vector is in the same direction as the kind of the rate at which the position vector changes, right? It's going to be tangent, and you just divide it by the magnitude to make it a unit vector. And what is ds? Well, here's the deal. We know ds is really just the magnitude of r prime of t dt, right? The speed times time, right? Or the magnitude of displacement times time, right? Because we know ds dt would be the magnitude, and you can arrange, right, multiply both sides by dt. So you see that these kind of cancel out, so you're going to be doing cf dot r prime of t dt. And this makes sense. R prime of t dt is just dr, right? That kind of, this makes sense. So, because we know dr dt, I'm just going to show it, is equal to r prime of t, right? So this is actually not too bad, right? Let's do a quick example. I'll do one example because I don't think these are too bad. Like this ain't too bad. Let's do this example. Let's do this example. Actually, it doesn't matter. Yeah, let's do this example. I don't want to do integration by parts again. So let's say we want to find, let's say we know that f of x, y, z, so this is like a path, or I guess a field in 3D. Let's say it's equal to x plus y I plus y minus z j plus z squared k. So this is our vector function. And let's say the r of t, the path that the particle goes through, is equal to or whatever it goes through, right? Whatever that path is, just t squared plus t cubed plus t squared. So t squared I hat plus plus t cubed j hat plus t squared k hat. And we want to find, let's say we want to find like, and the curve, it's from 0 to 1. So we want to find the line integral. So let's say, we're going to integrate, right? We want to find f dot dr. So the way we go about doing this is first we want to find, right, we're going to be working with r prime of t. So we got to find the derivative function. So r prime of t is going to be 2t I hat plus 3t squared j hat plus 2t k hat. And now what we can do really quickly is just sub in all the values here, right? So f, right, if we want to make this in terms of t, right, it's just going to be t squared plus t cubed I hat plus t cubed minus t squared j hat, and then it's going to be plus t to the fourth, right, because t squared squared k hat. All right. Now we just want to, what we want to do now is we want to take the integral, right? So we're going to integrate f dot, so we're going to be doing f dot r of t dt, right? So we're integrating from 0 to 1, f dot r prime of t dt. So if we're going to do f dot r prime r of t, or f dot r prime of t, then we just got to do the dot product. And the dot product's not too bad, right? It's just doing this times this plus this times this, right? So x components multiplied plus y components multiplied plus z components multiplied. So just to simplify this, I'm kind of do this stuff in my head, but hopefully you can kind of follow along. We just multiply 2t times t squared, so we're going to get, so 2t, we're going to get 2t to the third plus 2t to the fourth. And when I do the y components now, I'm going to get 3t to the fifth minus 3t to the fourth. And then plus, we're just going to get plus 2t to the fifth, all of that dt, right? So from 0 to 1, I'm going to have, so 2t to the fourth, so it's really going to be 5t to the fifth minus t to the fourth plus 2t to the third. This is just me simplifying. If you just add all the like or common like terms, I think that's what it's called. And this is pretty simple, right? This is just going to be 5/6 t to the sixth minus 1/5 t to the fifth plus 1/2. Right? Did I mess that up? Hopefully I didn't. And then we're going t to the fourth, 1 to 0, so we only worry about the coefficients because we're going from 1 to 0. So 5/6 minus 1/5 plus 1/2. What's a common term? I think I definitely messed this up. This is not the answer I got. Let me check my work. 1/3. Where did I get 1/3? So 2. Did I do this all right? Yeah, I think this all looks good. Two t to the fifth. Oh, because it's 2t to the fifth. Wait, but I accounted for that by adding those. Added that. Let me just check with my calculator. I know calculator is kind of cheating, but I just want to make sure I don't want to waste much time. Minus or plus half. Oh, okay, this actually is the right answer. This should equal 17 over 15, and it does. I guess I thought it wouldn't because I would have a base of 30, but I guess when it's all done and dusted, something will simplify. So yeah, this has been line integrals for both vectors and scalars. Hopefully this has made some sense and you're able to draw the connection to physics.